This is an explanation of the technical information on stars that shows up at the tail end of all of your constellation handouts. Some of you might be interested in making a 3D constellation. That's something I've had students do before, and I have directions on that, so we can talk about that later. But anyway, here's some of the information you might see about stars. This is actually for the first constellation of the week for spring, and the last constellation of the week for fall. So there's the constellation or the stars that belong to the constellation of Orion. This is the asterism that we know for Orion. Up above it is Taurus, and to the left of it is Gemini. So just for a sampling of some of the ones we'll learn this quarter. Oh, and there's a star in Taurus, Aldebaran. Betelgeuse is a star in Orion, Bellatrix, Rigel, and Saiph or Safe. I've heard it pronounced both ways. So first of all, just what is a constellation? Something you may notice on this picture are the dashed lines that are straight and make right angles with each other. Anything which is within the boundary of a constellation, within those dashed lines, is part of the constellation of Orion. Whether it's a visible star, a distant star that you can only see through a powerful telescope, or an asteroid that just happens to be in there temporarily, we would say that's part of the constellation of Orion at this time. It can also include galaxies that are very far away from us. It's just anything that from our viewpoint falls within those dashed lines. And so we'd say that's part of the constellation. The night sky, the celestial sphere that we imagine as some giant sphere that surrounds the Earth, has been divided into 88 constellations, 88 different areas of the sky. And they are not regularly shaped. They look like gerrymandered congressional districts or something like that, but that's just the way they got cobbled together by the International Astronomical Union. So, what is an asterism? An asterism is a recognizable pattern of stars. And so when you look at the stars connected with the yellow lines in Orion or Gemini or Taurus up there, those are the recognizable patterns of stars that we use when we identify which constellation we happen to be looking at. Keep in mind the constellation is the whole area that encompasses things, and the asterism is just the recognizable shape. Usually when I give my star quiz at the end of the quarter, I'll say, name the constellation that these stars belong to. So I'm not incorrect in saying that. Those stars will belong to that constellation, but they're not the entire constellation. Okay, here's what the data, or the table of technical data for the stars looks like for a particular constellation, and this is the technical data for Orion. The first column that's on here has the proper name of some of the stars that are in the constellation. Not all stars have proper names, nowhere near. There are way more stars than there are proper names to give them, so we don't even try. But a lot of them have historical names. Many of the names for stars are Arabic. When the Roman Empire fell, there were probably Greek and Roman names for many of the stars, but that knowledge was lost when the Roman Empire collapsed, and the Arab astronomers ended up being the ones who wrote stuff down for the next several hundred years, and they gave the stars their own names, or they probably used the ones that they had had all along. And so we have mostly Arabic names for stars. You don't have to learn all of the proper names for the stars. They're the ones that I want you to learn are on the sheet that you have available to you. In Orion, the four you need to learn are Betelgeuse, Rigel, Bellatrix, and Scythe or Safe. You don't need to learn any of the other ones on that list here. Okay, the next column over is something called the Bayer letter or the Theflamsteed number. I'm not actually positive what Theflamsteed did, but Johann Bayer in 1603 published a book, a star atlas called, I'm not sure how to pronounce this, Uranometria or Uranometria, something like that. And it's the old star atlas that you sometimes see pictures of. There were fanciful giants somehow connecting the stars, or some big twisty snake or something that was representing Draco, something like that. But it was pretty artistic. But what he did was he tried to give all of the visible stars in a constellation a Greek letter to designate it. And since there are only 24 Greek letters, and sometimes there would be more than 24 visible stars, he'd have to go beyond the Greek alphabet sometimes. We don't usually bother with most of those anymore, but for the first few Greek letters, which are usually the first few brightest stars in the constellation, we'll go by those Greek letters. And what we do is we'll say the Greek letter, alpha, beta, gamma, delta, whatever it happens to be, and then the Latin genitive of the constellation name. And for example, Orion, the Latin genitive is Orionis. And what we might say is, if we were talking about Rigel, we could also call it Beta Orionis. And that would mean the beta star of the constellation Orion, loosely worded. By the way, here's the Greek alphabet, and you can see all those different letters over there. You stick around in science classes long enough, you'll learn most of the Greek alphabet, because we use one symbol or another for just about everything after a while. We don't learn all that many in astronomy, but there are about half a dozen of them that we'll use fairly commonly. Anyway, there are those Bayer letters that show up there. So, and it's not uncommon to hear someone refer to Betelgeuse, for instance, as Alpha Orionis, or Rigel, you might hear Beta Orionis, something like that. Some stars are pretty well, people may not know their proper names that well, and sometimes you'll hear something like Epsilon Lyrae for one of the stars in Lyra, and it happens to be a nice thing to look at through a telescope. And so if you're out stargazing, you may hear somebody say, hey, take a look at Epsilon Lyrae tonight. So you'll hear that. The next two columns on here are part of a coordinate system that we'll learn more about later. I think I'm still going to try to have a lab based on that, although I don't know how I'll do it online. But the right ascension and declination are analogous to longitude and latitude. And right ascension is like longitude. Here's a picture for that. Let's see, I think I can show my little pointer here. Every star along this line here would have the same right ascension. And right ascension is measured eastward from a particular point on the celestial equator. It's actually the point where the sun crosses the celestial equator on the spring equinox. And so that's what the right ascension measures. And so everything along this line would have the same right ascension. On the other hand, if you were, say, over here, you'd have an arc for right ascension that came down this direction. Those stars would have a different right ascension. So that's the way that it happens to work. Declination is the number of degrees above or below the celestial equator. The celestial equator is the stars that are straight out from the Earth's equator in every direction. So they're the stars that if you're on the equator, they pass directly over your head at some point during the day. And the celestial equator is defined to have a declination of 0 degrees, just like the Earth's equator has a latitude of 0 degrees. And then the North Celestial Pole has a declination of plus 90 degrees. The South Celestial Pole has a declination of minus 90 degrees. Now, with latitude, we might say your latitude, for instance, Moses Lake is 47 degrees north latitude. Okay. With declination, you'd say plus 47 degrees. And if it's plus, it's above the celestial equator or north of it. If it's minus, it's south of it. So stars between the celestial equator and the North Celestial Poles have declinations between 0 and 90. Stars between the celestial equator and the South Celestial Pole have declinations between 0 degrees and minus 90 degrees. We'll have a day where we'll look at the, or a lecture or video, where we'll look at the celestial coordinate system, and you'll learn it in more detail at that point. Okay, let's see. We've got the first 4 columns taken care of. The next column is the magnitude of stars, and this is a measure of brightness, and it's an odd measure. It didn't used to have the decimal places in here until people started aiming telescopes at stars and feeding the light from them into photocells where they could actually get some kind of a voltage reading. Originally, the magnitude scale was developed by Hipparchus, one of the ancient Greeks, and he said, okay, the brightest stars we'll call first magnitude, the next brightest stars we'll call second magnitude, and then after that comes third magnitude, fourth magnitude, and so forth. And it's like the prizes in a cross-country race, first place, second place, third place, and so forth. But once astronomers started measuring the stuff from the stars, they could see that, for instance, a star with a magnitude of 1.72 was different from a star with a magnitude of 1.9. And there are some that are even closer together than that. But when you're feeding the light into a photocell, you can determine it very precisely. And so that's what they did. Also, it became apparent that some of the stars in the sky are brighter than other first magnitude stars. And when they started measuring it carefully, the scale went all the way down to 0 and all the way to negative numbers. So here's the way the scale works. The larger the number for the magnitude of a star, the fainter the star happens to be. With the naked eye, you can see to about 6th magnitude. Things that are 7th or 8th or 9th magnitude you can't see with the naked eye. You can with a pair of binoculars see quite a ways farther or quite a bit dimmer, but not with the naked eye. Then the very brightest star in the sky is Sirius. That's one that we'll learn here in our first batch of constellations, and it's at magnitude minus 1.7. The more negative the number, or the larger the size of the negative number, the brighter the star is going to be. But Sirius is the brightest. And it's really the only one that has a negative magnitude. There are a few stars that have magnitudes of 0. Other things can have negative magnitudes. Venus, at its brightest, has a magnitude of about minus 4. And it's actually bright enough to cast a shadow if you're in a dark enough place. But that's what the magnitude is. It's just a measure of the brightness as it appears from Earth. Now, since the stars are at lots of different distances, you can have a not so bright star real close to us, will look bright, and you can have a very bright star a long ways away, and it's going to look dim, so it doesn't take distance into account. The last column on here is the distance to the stars in light years. A light year is a unit of distance. When you took algebra, you probably learned an equation d equals RT, distance equals rate times time. Well, measuring distance in light years is measuring it in rate time because the rate is the speed of light and the year is the time. And the distance in light years to Betelgeuse is about 700 light years. That's 700. The distance would actually be 700 times the speed of light times 1 year. A light year is how far light travels in a year. So if you go out and look at Betelgeuse in 2020, you're seeing light that left that star in about 1320. Okay. Alnilam, let's see, that's one of the stars in Orion's belt, 2,000 light years away. The light from that star left the star. If you see it at night, you're seeing light that left in about 20 AD. So pretty amazing for the distances to some of these stars.